All right, so today's lesson, AP Calculus AB, this is the mean value theorem. It's also, you'll see it represented as just capital M, capital V, capital T. And on your AP Calculus exam, if you just write capital M, capital V, capital T, they'll know that that means the mean value theorem. All right? So, the mean value theorem. Okay, the mean is average, right? When we talk about mean in math, that means the average. And so we're going to be talking about average value theorem, the average value theorem. And of course that word average has to do here with rate of change. And what is rate of change when we talk about calculus? That is, rate of change is associated with slope of a tangent line to a curve, right? Or the derivative, right? Okay, don't get psyched out here. Rate of change, derivative. Instantaneous rate of change. Now there's instantaneous rate of change, which is what the derivative is, right? Instantaneous. But there's also average rate of change for, for some kind of situation. So if we have a graph like this, and here's where it started. That's the initial value, and here's the final value. The average value for this function would be this, right? The total change in y divided by the total change in x. That's the slope, right? So that's the average rate of change of the y with respect to x. So what the mean value theorem is doing is we are connecting derivatives, okay, we're connecting derivatives with average rate of change. So average rate of change and derivatives, we're combining them sort of together. Okay. Now, the mean value theorem is based on two hypotheses. Okay, so H1 is hypothesis 1, and this is sort of what we're assuming at the beginning. We're assuming that for this function that we're talking about, like the one I drew before, and I'll just simplify it a bit over here. Okay, we're assuming that it is continuous on the interval from A to B. Okay, so it has to be continuous in order for this theorem to be used. It also has to be differentiable. And so what differentiable means is that it can't have any sharp corners or points, right? And obviously if it's continuous, there's no gaps. So it has to be differential. It has to be smooth. We can't have a cusp or something like that. It cannot be like that. Then this mean value theorem will not be able to be invoked, okay? So these are the two hypotheses. They have to be continuous, have to be differentiable. All right, so if that happens, this right here, and I'm going to bring this sort of kind of up into the main body of the notes here a little bit. This C right here, this is actually the theorem. Okay, this is the conclusion. And I'm going to take a few minutes just to explain what this means. But if this is the case and this is the case, there exists a number C somewhere in the interval. Okay, so somewhere in between A and B, such that the instantaneous rate of change evaluated at C is equal to, and this right here is sort of the average value for the entire function. This is the slope from beginning A to end B, okay, which is the slope of the line connecting f of A and f of B. So like I drew up there before, the slope or the average value of the function, and the average rate of change of the function over time, or whatever we want to call that, change in y over change of x, that there exists some point, some value C, for which the tangent line is the exact same. So you can probably see that. I mean, if I give you some tangent lines here, right? If I give you some tangent lines here, you may be able to see that there in between A and B, that there's at least one tangent line that would be exactly parallel to this red line. See that? And if the function is continuous, and if it's differentiable on all points, then this will happen every time. That at some point, and it looks like right around here, there's going to be a tangent line that is completely parallel. See that? And maybe over here, tangent line that's parallel. All right, does everyone see that? These are the two lines right here that would appear to be exactly parallel to this red line. So that means that there's at least one, and there might just be one or there might be two, but here is a C value, and don't mistake that for a critical value, please. But it's just a C, a constant. So there's the first C, there's the second C, where the slope is the same as the average slope for the function. And that's what this means. Okay. So what we could do is we could actually give some values here. And actually, maybe what I'll do before I give values is I'm going to draw just a few more examples, right? So we've got A, and we've got B, and I've got, a function that looks something like this, right? Okay, even that. The average value here would be the slope of the line connecting these 2 points. It's the average change from A to B for this function. And there's got to be somewhere, right about, I don't know, about here, there's got to be a point where the tangent line is exactly parallel. See that? And that would be the point there. There's got to be at least one. Now, do you understand that there may not be, it may not be true if it's not differentiable. Like let's say this is the starting point here, this is the end point. Okay? This is the average value there, right? That's the average slope there between those two. But if it's not differentiable, these derivatives, and this one kind of, this is undefined right here at this point, and then they come down like this, and then, oops, we didn't have one that was pretty close to 0 there because it's not differentiable, you see? So this is very different than this. The slopes here will have to come to 0 and then go back down. These ones, they just kind of keep going up, approaching infinity, and then infinity coming down, right? See, there's no 0 now. So it's got to be differentiable. And numerically, we can figure this out. So let's just pause for a second and we'll do some questions. Okay, so if we take a look at this question, which I've had a chance to copy down here, it says this: let f be the function defined by f of x equals x cubed plus x minus 4. What is the value of c for which the instantaneous rate of change, and we see that right away, and we're thinking f prime of x, right? For the instantaneous rate of change of f at x equals c, so we're trying to find the x value, or which equals c, that has the same as the average rate of change of f over this interval. So that's basically, we're using the mean value theorem to say, here's the equation of the graph, find the value c that has the same slope of the tangent line, that's the instantaneous rate of change, that has the same slope of the tangent line as the average rate of the entire function over this interval -1 to -3. So now some of these questions will be in sections on the AP exam where you cannot use a calculator. This one says you can use a calculator. So I just graphed this. You don't have to graph it, and we won't use the graph per se to answer this question. But if you look at this graph, right, you guys see that? If we look at this graph, this is sort of what it looks like from here's x equals -1, and here's x equals 3. Okay? So if we were to draw an imaginary point there, and I'm just going to copy this screen actually so I can write on it. Right? So let's just put this right about here. I'm going to go over top. Okay, it doesn't like going over top. That's fine. Oh. So here's my screen, and so what we're looking at is here's the equation at -1, right? And it was -1. Yeah, -1 to 3. And then, so 3 would be up here somewhere. Okay? So we're looking at this average rate of change for the function. Everyone understand that? So this is the slope, and we're going to calculate the slope. And we are looking for some value for c. Okay, where is it? Right here? No, where is it? Right about, maybe about there. Okay, it's going to be pretty close to, x equals maybe 1 point something. Okay, that's what we're guessing. And so we're going to try, first of all, find the slope of the line. Okay, from this beginning point to this end point over here in the interval. And then we're going to find the derivative and let the derivative equal that slope. Solve for x. So then find the x value that gives us that slope. So you would tackle the question like this. Let's first of all find this average rate of change for f. And so we're going to go f of 3 minus f of negative 1 all over 3 minus negative 1. And we're going to calculate the slope there. And so f of 3, okay, so that's 3 cubed is 27 plus 3 is 30 minus 4 is 26 minus f of negative 1, well, that's negative 1 cubed is negative 1 minus 1 is negative 2 minus 4 is negative 6 all over 3 plus 1 is 4. So this slope is going to be 32 over 4, which is going to give us 8. Does everyone see that? So that is this slope right here. So we have a slope of this line, m equals 8. See that? Negative 1 to 3. That's the first step. And the mean volume theorem says that if this is continuous and differentiable, which I didn't talk about that before, I guess we assumed that, but yes, it's continuous, there's no gaps, there's no restricted values for x, right? There's no discontinuities. It's a cubic function, so we know that those are pretty smooth, right? They don't have any cusps or corners or asymptotes or anything like that. So we're good there. So we go ahead and we do this, and you can graph it just to be sure. So now what we want to do is we want to find the derivative over here. So f prime of x equals 3x squared plus 1. And I want to let that equal 8. And then here I want to solve for this x that will be the constant that will give us the slope of x. See? So this is the expression for the slope right here. And I want to find the x value that has the slope of exactly 8. So when we go ahead and do that, we're going to subtract 1 from both sides to give us 7. This is going to be 3x squared divided by 3, and then take the square root. It's going to give us x. It's going to be plus or minus 7 over 3, and we're going to talk about which one that would be. Was it going to be plus or minus? Yes, thank you. Plus minus root 7 over 3. You get thrown off when the principal comes in the room. All right. So plus or minus root 7 over 3. Now, which one is going to be? Is it going to be the positive version or the negative version? Well, remember, this is from negative 1 to 3. So if you calculated the square root of 7 over 3 here, right? And again, if you're unsure about this, just give it a try. Square root of 7 divided by 3. What is that? 1.5. So we're looking at positive 1.5, which is pretty close to what we guessed, or negative 1.5, and you're going, whoops, that's outside of our interval, so what's it going to be? X equals positive root 7 over 3. And of course, in this question that I gave you, it's multiple choice, so here we go. Here's our answer. Okay? So the constant is this x value, positive square root of 7 over 3, which is about 1.5, which makes total sense compared, looking at our diagram. Any questions about that? Yes, no? Good? Okay, that's example number 1. Let's try example number 2. Example number 2. So I'll give you a second to copy this out while I read it aloud. It says, if f of x is x cubed. So we want to draw a quick sketch of that over here. x cubed looks something like this, right? At what point on the interval 0 to 3, okay, so we're just going from 0 to, let's say, 1, 2, 3, over here, is the tangent to the curve parallel, so having the same slope, as the secant line for this interval. So when we talk about average rate of change for the function over an interval, really what we're calling this is a secant line. That's what it is. Now don't get this confused with the trig secant, okay? It's not 1 over cosine. But a secant line is just basically a line connecting 2 points on a function, okay? You might have first learned about it in grade 9 or something like this, where this is a secant line right here, from here to here. So it just intersects sort of the curve in question at 2 points, and this would be a secant line, okay? So that's what we're talking about. So parallel to the secant line to this interval. Just get used to this wording. You might see this wording on the AP exam. So if we're sketching this out, we're basically looking for a tangent line that has the same slope, right? So somewhere around here is what our guess is going to be. But how do we find that out for sure? Well, the same process holds from, just like we did in example 1. So remember, you always take the far right boundary there, 3. So f of 3 minus f of 0 all over, and the x values, of course, themselves were 3 minus 0. So f of 3 is 3 cubed. That's 27 minus 0 cubed is 0 all over 3. And so this equals 9. So we have a slope here, m equals 9. So I want to find the x value that gives us the same slope. So we're going to have to take the derivative of f of x. And what is the derivative of f of x? 3x squared, yeah. Okay, remember, you're getting integrating and differentiating mixed up here. That's no problem. So 3x squared. And I want to let that 3x squared equal what? I want to let it equal 9. Right? So 3x squared equals 9. X is root 3. Again, plus or minus. Well, there's no negatives in the interval, so it's got to be the positive version. And so there's your answer right there. Root 3. Okay, does that make sense? Okay. All right, let's go on to example 3. This one would probably be one of the tougher ones, I would say. Just got to think about a couple extra little things here. Dealing with sine. So this question says, if f of x equals sine of x over 2, and yes, that's an x, it's not a pi. That's an x, okay? At what point on the interval, so with x values here, pi over 2 to 3 pi over 2, is the tangent to the curve parallel to the secant line for this interval? And again, you're not supposed to use a calculator for this one. So we won't use a calculator here. We won't look at the function, although, you know, sine of x, you know what sine of x looks like. So sine of x over 2 probably going to look fairly similar. I don't know if you remember to curve sketching, right, earlier in calculus course here. The curve sketching was, this would be sine of 1/2 x. And so this value right here did something to that sine graph. Remember that? Yeah, it should be a horizontal stretch, right, by a factor of 2. Okay, so we have an idea of what this looks like. And for x values of pi over 2 to 3 pi over 2, we're going to be able to figure this out. So what do we do first? Well, we want to find out what the secant slope is. So we're going to do f of 3 pi over 2 minus f pi over 2 all over 3 pi over 2 minus pi over 2. So this here, and I'm going to show some work here. So this is sine of, now remember x here 3 pi over 2, is actually divided by 2. So this is sine of what? 3 pi over 4. When you divide something by 2, you double the denominator there. Minus sine of pi over 4. And it's going to be over pi here. So, sine of 3 pi over 4. Can't use a calculator, can you? So what's the handy diagram or chart that we have used in calculus and pre-calculus 30? Unit circle, right? Okay. So the unit circle needs to be your friend, okay? And you need to try and envision and picture what these values are. So for pi over 4, that one's easy. That's half of pi over 2. That's 45 degrees, right? So what's the sine value for pi over 4? Yeah, that's right. The points are root 2 over 2 and root 2 over 2. It's the second value, always, that's sine. It's cosine, alphabetical. CS, cosine. So this is root 2 over 2. Now, the 3 pi over 4 is over here, right? So what is the sine value here? Well, remember, the values in the unit circle are connected. This is negative root 2 over 2, comma, positive root 2 over 2. So what's the sine value for this one? Same. Exact same. So what we have here is we have 0 on top. And of course I'll write that out, but we have root 2 over 2 minus root 2 over 2 over pi, so this equals 0. So again, if we're looking at this, whoa. That's what happens when I accidentally squeeze a button on my pen here. So if we're looking at, try that again. You know, a sine function, and this is, it's been stretched a little bit, so you know, we're basically kind of looking here and here, it looks like, right? Because it starts at 0, and then you're going up to a maximum point here. So on the way to the maximum point, you've got this point right here, and then you hit your maximum point, and then you start coming down. So it looks like it here. So it makes sense, doesn't it? It's either the same y values, so the slope is 0. 0. Good. So I need to find, right? I need to find the derivative here of this. That's what's next, right? So f prime of x is what? Who remembers what the derivative of sine is? It is cos. Now, it's cos of x over 2. When I take the derivative, what else do I have to do? Yes, chain rule, so I have to take the derivative of the inside function as well. So what's the derivative of x over 2? 1/2. That's right. So here's what I got to do. I got to let this equal 0. Okay. Now this is where it gets a little tricky. Okay. I don't know how much you remember about this trig stuff, but if we were going to let 1/2 cos x over 2 equals 0, that half is gone, right? You multiply both sides by 2, well, 2 times 0 is still the same. So it's the same as this half being gone. So we don't need that there. Same as this. And cos of x over 2, if you kind of forget about how this whole thing works, you know, with the stretching and x over 2 and what is that? I would encourage you just to do this. Just say, hey, let's let w equal x over 2, and then I'm just going to go ahead and do this. Cos of w equals 0. So where does cos of w equal 0? Go back to your, right here, go back to your unit circle, right? Cos of what value equals 0? Yeah, pi over 2, 3 pi over 2, right? So what we have to sort of be careful of here, yeah. So what we have to be careful of here is we're looking at this for x values, but this is w. So if we tried, if we just said, okay, well, w could be, we said pi over 2, or it could be 3 pi over 2. let's find out how that translates into x, because that's what our domain is, right? X. So what does that mean? Well, that means that pi over 2 equals w, which is x over 2. And so what is that? X equals pi. And also 3 pi over 2 would equal x over 2. And so x equals 3 pi as well. So which one of these fall in the interval that's given? Between pi over 2 and 3 pi over 2. Or between here and here. Which one of those? Pi. So pi is going to be your answer right here. Okay. Now I did locate the solutions as well, so I will show you what their solutions were. It might be, I mean, they're the same as ours. We've done all these questions correctly, but there's a solution to number 1, if you want to compare that with your notes. Or here's a solution to number 2. And here's a solution to number 3. I think I cut off the very end here. All right. So again, these are the kind of questions that they're going to be asking for mean value theorem. They also may ask you some real comprehension questions, so you may have to explain how the mean value theorem is used in a certain situation. But if you remember this the basic premise here, right here, that if it's continuous, the function, and if the function is differentiable on the interval, then there will exist some constant that has a tangent line slope equal to the average slope of the function over the interval. That's the bottom line. That's what the mean value theorem is. That's kind of its basic form, and those are some questions involved in the mean value theorem. Do you have any questions?